Yeah, so welcome to the second lecture. So today we want to continue talking about a linear regression, and then we will do a really explicit example in Python and implement this gradient descent, but also in the end talk a little bit about linear algebra and see how we can solve this linear regression by just using linear algebra without using this gradient descent. So recall, oops, no, not this, recall this. So last time I gave an overview over the field of machine learning, and there were different subfields of machine learning. And so there were three main subfields. So it was supervised learning, unsupervised learning, and reinforced learning or reinforcement learning. And last time we started with this supervised learning. And supervised learning, there were two subfields, regression and classification. And we started with talking about regression. And next time we will do an example in classification, and then later go on to unsupervised learning and also do reinforced learning. And there I want to maybe do some game AI where you teach a program to play some games. But first we need to do the basics here, which maybe is not so much fun, but it's really important to also learn the fundamentals. So recall that in supervised learning, these two classes, classification and regression, so there were two main differences between these two types of machine learning. So, and the difference was the output. So in the classification case, the output of our machine or of our program was always something discrete. So there were different classes. And in the regression case, the output of our machine or of our program was something continuous, which means it's a number which can take any value between, that can take any value. And yeah, so, and the example we talked a little bit about last time, and which we will solve today in detail, was this example of Tebasaki-Eaton. So the setup was that we ask some people on the street in Nagoya how long they live in Nagoya, and then we ask them how many tebasaki they have eaten. And in this case, we have 6 data points here. So for example, here's a person who just lives 2 weeks in Nagoya, and he ate or she ate 5 tebasaki, but there's also a person living here for 30 weeks, and he or she ate like 37 tebasaki. And we see that there seems to be some relationship between the number of weeks living in Nagoya and tebasaki eaten. And the observation was that this might be some linear graph like this. So what we want to do, we want to use these data to train a machine to create a program which makes a prediction that if we give this program the number of weeks we're living in Nagoya, it makes a prediction on how many tebasaki we have eaten. And this is an example of supervised learning and is also an example of regression. So we have this. So we introduced these words last time, that asking these people on the street, this gave us some training set. And the training set was a collection of training example. And a training example was given by, in this case, a weeks living in Nagoya. And this we called a feature. And then we had the number of tebasaki eaten, which in this case is called the target or label. And we wanted to find a learning algorithm which creates out of these training sets a program. And this program we call the hypothesis. So this will be a function. And then in the end, this function will give us the number, or it gives a prediction of tebasaki eaten whenever we give this function the number of weeks living in Nagoya. Okay. And then to write this problem down more precisely, or to write down our learning algorithm, we introduce some notation. So first we introduce this input values, or this feature space, which we denoted by X, and the output values, the label space, by Y. And then in this case, in training example, so a pair of weeks living in Nagoya and number of Tebasaki eaten is then an element, a tuple in this product here of this input, of this feature space and the label space. And the training set is then just a collection of training examples, which is just given by a tuple like this. So in this case here, we have n training examples. So it's an element in this space here. And what we want to create now is a function from the feature space into the label space. And because we call this a hypothesis, we also denote this by h. So h will be a function from x to y. And a learning algorithm is then an algorithm which creates such a function out of a training set. And we picked one particular learning algorithm. So we saw in this example here that the data looks like that there's a linear relationship between the weeks living in Nagoya and the number of Tebasaki eaten. And therefore we created a certain model. So we introduced this notion of linear regression. And in general, this means that we say that our hypothesis has a certain shape. And so this function we are looking for will depend on some theta, which we call parameters or also weights. And these will be just a collection of numbers. And then the model for our hypothesis is given by this sum here. Because in our example, what we will be looking for is we have the case that d equals 1. So we just have one feature, the weeks living in Nagoya. And in this case, so in this case, this theta, we are looking for two numbers, theta 0 and theta 1. And in this case, this h theta of x is just theta 0 plus theta 1 times x. So this is just a linear function like you learned in school. And this x here, because we want to write it in this way, we will also introduce this x0 here. So here we also have an x0, but we use the convention that this x0 is always 1. So the x we plug into our hypothesis will always have two values, x0 and x1, but x0 will always be 1. So this x here is always a vector of size d plus 1. So in our example, it's size 2, but this x0 is always just 1. So this is just to make the programming later easier and also the formulas. So here this will really just, the input is basically always just a number. Yeah. Okay, and then the goal is find parameters. So the goal is to find two numbers, theta 0 and theta 1. And then we introduce the notion of the cost function. So, I mean, we need to decide which thetas are good and which thetas are bad. So, so what we want to have in the end is some h of theta x such that this looks like this. And to decide which of these thetas are good and which are bad. So for example, this could be for one theta, but for another theta. So this could be some theta prime, h of x. Clearly this orange theta here gives a better approximation of these data, or a better hypothesis than the green line. And the way we want to measure this is we want to measure here the differences between the training set and our function, which in this case, if I sum up these red lines, then this is smaller than, well, than summing up these lines here. And to measure this, how good a theta is, will be done by this cost function. So the name is cost function because the higher the cost, the worse our thetas are. And there are different ways to define a cost function. And the one we choose here is given as follows. So if we have a training set, then so we fix a training set. And then our cost function will be a function where we plug in thetas, theta 0 and theta 1. And then the cost function tells us a number. And if this number is high, then the theta 0 and theta 1 is bad. And if the value is low, then the theta 0 and theta 1 are good. And the way we define this is we take so j of theta is given by this sum here. And this sum runs from 1 to n. So it runs through each training example. And for one training example, it calculates the value of the hypothesis at the feature and compares this hypothesis at this feature with the label of this trainings example. And so this will be the red line. So, and this difference might be positive or negative. And then we square this. So these objects will always be positive. And the bigger the difference is, the bigger this number here is. And then we sum all of them up. And therefore this function here is big if the difference between the value of the hypothesis at some feature differs a lot to the corresponding label. And what we want to do is we want to minimize this function j of theta. And in general, this j will be a function from rd plus 1 because we also have, so the theta starts at theta 0, theta 1, up to theta d. And as an output, this here will always give a real number. And then at the end of last lecture, we, so first of all, we will talk about two ways to solve this problem. So one way is by using linear algebra, and there's an explicit formula which we can write down in the end and say, if we have this training data, then theta equals blah, blah, blah is the perfect solution. So this we will do today at the end, but there's also an algorithm to approach the perfect or the best theta step by step. And this we will also use for other learning algorithms later, where this perfect solution does not exist. And therefore we want to use this linear regression to understand the basic principle of this algorithm called a gradient descent. And this we also did last time. So the main idea of gradient descent is, so we want to minimize a function. So if I have some function here, let's assume this is j, then I want to minimize this function. And to do so, I start at some point, at some theta, and I evaluate this function at this theta. So here I have j theta. And then I look at this point at the derivative of this function. And depending on, in this case, if the derivative is positive or negative, I will change this theta. So in this case, the derivative of this function here is positive. Therefore, this theta I should make a little bit smaller. So then in the next step, I will get a new theta. And then I can evaluate the value j of the new theta and can look at this place and see, oh, the derivative is still positive, so I should still decrease this and get a new theta, j. And then I can go on and go on. So at some point, maybe I will be here, and then I see here the derivative is still positive, but then maybe I will make it smaller and land here and see the value there, and then see the derivative is negative, and then I go to the right, and in the end, I will land here. And so this is the basic idea, but in our case, this here would be a function from R to R, but in our case, this cost function is a function from R d plus 1 to, so in general, this is a function d plus 1 to R. So there one needs to say what we mean by derivative and how to decide if a function goes up or down. And this is then given by the so-called gradient, which some of you learned in calculus, and some of you will learn it in calculus. But the gradient is actually not so complicated. So here we can see the case d equals 1. So here, for example, this j is a function from R2 to 1. So as an input, this gets some theta 0 and theta 1 and sends it to the cost function of, so if this is theta here. And so if we start at some point here, so here we have, maybe let's say here, let's say we take a theta 0 here and some theta 1 here. So at this point, I can evaluate this function. So here I have this j theta 0, theta 1. And now I want to decide at this point here, maybe the picture is not so nice here. In this case, where should I go? And so if I stand here on the hill, I need to decide in which direction I go. And in this case, for example, here we see that in this direction, it goes up. So we should go in the other direction. And the way to decide in which direction we should go is by using the so-called gradient. So the gradient in this case here, which is denoted by this nabla, so the gradient of j at some point theta is a vector, in this case of size 2, where in the first component we take the derivative with respect to theta 0 of j, and in the second component we take the derivative with respect to the second variable and then plug in theta. So at each point, for example here, it could be that the nabla j of this particular point here. So I hope this is not confusing. So sometimes I write theta and sometimes theta 0 and theta 1. So this theta is always the vector with values theta 0 and theta 1. So here, if I evaluate at this blue point here, the gradient, then maybe in this case, it will be a vector which maybe shows in this direction, because here we see in this picture that the value goes up. So maybe here it could be that maybe it goes in the direction, I don't know, -1, -1. So here this goes positive, and I know. So maybe in this, so here theta 0 goes up. So in this direction, maybe maybe we have something like this. Then this would be exactly here the vector which shows in this direction roughly. Anyway, the statement is that if I have some function like here and I calculate the gradient, then the gradient always shows in the direction of the steepest ascent, so it shows in the direction where it goes up. And of course, we want to minimize our function, and therefore we take the gradient, we look in this direction, and then we turn around and take a step in the opposite direction to make the function smaller. So yeah, so this is another picture. So we will see in the Python example that in our case, that our function will actually look exactly like this. There will be just one minima, and it will be, because it's a quadratic function, our cost function, so we will have a picture like this. But this we will see later in the Python example. So and then the general idea of this gradient descent is, so this is now the algorithm we want to understand. So we start at some point. So we will start at any point. For example, we start at 0, 0. And then we get some value there. And then at this point, we calculate the gradient, which maybe shows in this direction. But we then go in this direction one step and get a new point here. And then again, calculate the gradient and get a new point here. And then in the end, maybe get a final theta, which gives us here the minimal point. So in general, if we have d features, then our gradient of our function will be a vector of size d plus 1. And the entry the entries are just given. Oh, there's a typo here. The entries are just given by the partial derivatives. And the algorithm is then, we start at some point. We start with any theta, for example, 0, 0, 0, 0. Or maybe we already have a good guess which the theta could be. And then what we do is we say the new theta is the old theta minus, and then we take some multiple of the gradient and subtract this. And this alpha here is called the learning rate. And depending on the size of the alpha, we will make a big step or a small step. So if we choose the alpha too big, then if we go to the example here, if we would choose an alpha which is too big and we start here, and we see we should go in this direction, and alpha is really big, then maybe we make a really big leap and land here. And then here we see we need to go in this direction, and then we jump back. And then if alpha is too big, we would just jump around between these 2 points. And if alpha is too small, then it would really take some long time until we land here at the minima. Yeah, and so this we do several times, because one time doing this is just one step, and this alpha will say the size of the step. And this we will do until we are satisfied. So this could mean several things. So either we could say we do it until the value of this j of theta doesn't change anymore, or we just say we always do 1,000 steps. And yeah. Okay, and now before we go to the implementation, we want to calculate this gradient in our example, which can be done really explicitly. So for this, I will change my paper. Okay. So we want to use this formula here. And to use this, we need to calculate this gradient of our function j. So now let's do some calculation. So recall our cost function is given by this, and the gradient is defined by this. So what we want to calculate is the partial derivative of our cost function with respect to one of these variables. So we want to calculate the partial derivative del theta j of this cost function j of theta for all positions. So this j will go from 0 to d. So now we need to check what this is if we apply this to this function here. And this will be just standard calculus. So, I mean, what is this? So this is, we take the derivative of, so now I just plug in our cost function here. So we take the sum over all trainings examples of h theta xj minus yj squared. And so now, well, what is this here? So now we want to take the derivative of this sum here. But we learn in calculus that if I take the derivative of a sum, then I can just take the sum of the derivatives. So I could copy this here, and I could change the derivative and the sum. So this is no problem. And now, how do I take the derivative here? So here I have an inner function which depends on this theta, and I have some outer function here. So for this I need to use the chain rule. So recall that if I take the derivative, let's say del x of g of f of x, then this is just the well, the derivative of g of f of x times the derivative of the inner function. And here in this example, our function outside is just x squared. And here we see why we have this factor 1/2 in our cost function. So last time I mentioned we include this because later we want to take the derivative to make formulas nicer. But of course, this doesn't make any difference really in our problem, because if we want to minimize the cost function, then this factor 1/2 doesn't play any role. But now we see that if we take the derivative here of this function outside, and we get this factor 2 here, which cancels out with this 1/2. So if we now apply this chain rule here, this 1/2 gets canceled out with the 2. So I get, so the sum is still there. And yeah, and in this part here, so this 2 becomes a 1. So I just have this here. So this just stays h of theta x j minus y j times. And now we need to take the derivative of this function here. But what is h? So this h here, by our model, we said this is theta 0 plus theta 1 xj1 plus theta d xj d. So if I take the derivative with respect to theta j of this function here, then everything vanishes except for the term where I have theta j. So for example, if I take the partial derivative with respect to theta 1, then the derivative of this here, everything vanishes, except for this here, And the derivative of this with respect to theta 1 is just this xj1 in this case. So in this case here, the only thing which survives, if I take the derivative with respect to theta j, oh, sorry, I want to use an I here. So this I, because here in the sum I use j, sorry. So I want to take the derivative with respect to theta I, sorry. So the only part which survives here is the xj I. So it's xj I. Sorry. So the j here runs over the trainings examples, and this I here runs over the features. Oh, there's a suggestion in the Menti chat. How about using some different index for sigma? Which sigma? Oh, you mean this? I don't understand the question in Menti. Sorry for. But maybe it was about my problem with J and I. Anyway, so this is the final result, stating that if I have the cost function, J, and I take the derivative with respect to theta I, then in the end, I get this sum here, which sums over all trainings example, and it always just multiplies this difference here, which in the picture was the red line, with the ith feature of this trainings example. But don't worry, we will implement this in a second and make it more explicit. So what this means in the d = 1 case, so maybe I copy this here. So if d = 1, our j goes from R2 to R. And in this case, the gradient of j, so this theta is just theta 0 and theta 1. So this will just have 2 entries. So it will be the derivative with respect to the theta 0. And it will be here the second entry with respect to theta 1. So in this example, the gradient is just a vector of size 2. And here, according to this formula, the first entry of this sum, so we still take the sum over all trainings example, and here calculate our function h theta. But maybe in this case, I can also write it down explicitly. So here we just have theta 0 plus theta 1 times xj minus yj times, and here would be now the case I = 0, but in this case, this is just 1, because this is just a convention that this one is just 1. So here the entry is just given by this sum here. And the second entry is the same sum, but here we have theta 0, theta 1, xj minus yj. And this we multiply by x. J. And here, in this special case, we just have one feature. So more precisely, this would be xj1, but in this case, we just say this is the one number we have x of the trainings example xj. So most of you are maybe now familiar a little bit with Google Colab, and I also shared this notebook in the Discord chat. And what I want to do now is everything we just did before now in Python. So this first code here should be familiar to you from the test assignment. So we have this training set here, so which are just two arrays, but I renamed this a little bit now. So tx are our x, xj. So this is x1, this is x2, up to x6. And these are our y's. And then this code here is just to plot this data. So if we execute this code, we get this picture here, which gives exactly the graph from the lecture. And we want to find the line which gives the best hypothesis. And this I learned now from one of you. Someone already implemented this also in the test assignment, because there's of course already a function which does exactly what we want to do. And this is included in this NP. So this NP here is NumPy, which is a package, or one package for Python to do mathematics. And there's of course already a function which is called Polyfit. So this in general makes polynomial fit for some data points. And here this entry just says we want to have some linear interpolation of these data points. So this will return two numbers, which are exactly our θ0 and θ1. And then what this function here does, it just plots this function here, θ0 plus θ1 times, and then the corresponding x values. So if I execute this now, we will see that what we get here is exactly this line, which we want to find now by ourselves without using this already implemented function here. And we can also check, in this case, for example, we can see what these values are. So here we see these are actually the values we are looking for. So the θ0 will be 6.4 and the θ1 will be 1.05. And you see in the graph, this is exactly, if there's 0, we are around 6.4 here. And here, if I go 1 to the right, I go roughly 1 up. So this is almost has derivative 1. Okay. But this orange line we now want to find by using the gradient descent. So then we learned that what we want to do is we define this function h, which is given by the sum here of the theta's and the x, where the sum runs over all features. So the goal is to find these theta's. And we are in the special case when d is 1. So we really just want to find θ0 and θ1. And we also defined this cost function here, which sums over all trainings examples. So how would you write down, or one possible way to write down this hypothesis? So this hypothesis is a function which depends on two things. It depends on the theta and it depends on the input x. So here, this is the way to define a function in Python. So I say I define the function x, and as an input, this function gets theta, and I define the function h, and as an input, it becomes theta. It gets an theta, and it gets an x. And what I want to do now, there are probably much nicer ways, but to implement the sum here, one way is to say I write this sum into this variable ret, and I return this value in the end. And now I go through each trainings example here. I mean, I go through all features here. So in general, this d here will correspond to the length of theta. And so what I do here, for each position, I just add theta I times xi, which is exactly here the sum on the top. And so this is our training set. This is the same as before. And the number of trainings examples is just, so this len here just gives the length, which in this case is our n. And our n in our example is just 6, because we have 6 trainings examples. And then the cost function j, this function here, depends now on this theta. And there we do a similar thing. We just say this is, so this here is the same as here. I just wanted to use 2 different notation to just show it. So if I have a variable and I add something to this variable, I could also just say this plus equal. So instead of this, I could also just write ret equals ret plus blah, blah, blah. And here I just take 1/2 times, and then I evaluate this h at theta and x. And here the input of this h is this vector theta and the vector x. And in our case, when d equals 1, both of them have size 2. So theta is theta 0 and theta 1. And this x is x0 and x1. But x0 is always 1. So here as an input, I have x1, which is x0, which is 1, and the actual value of our feature. So this is tx at the place j, and minus the label at the place j. And here I just take the square. And another way one could write this would be, so I just want to introduce different notations. I could also write it the square, and in Python you can also just write with 2 multiplications and a 2. So this is also just the square of this expression here. And instead of this plus equal, I could also write this is ret plus this. So these 2 lines do exactly the same. Okay, and so now let's run this code here. So what I do here, so this T0 and T1 are these values which we already got here. So the best possible values. I just want to show what the cost of what is the best possible cost. And so here, so in this line here, I just evaluate the cost function at the best possible case. And then I also evaluate the cost function at some other place. So if I run this, then we see that for our good thetas, the cost function is 115. And at some other place, the cost function is 228. So here the cost function is, of course, smaller than the cost function at some other choices for theta. So for example, this here, what I draw in the beginning could correspond to this orange line, and maybe this here could correspond to the green line, which is a little bit worse. And what we want to do now is minimize this cost function by using this gradient descent. And for this, we could first plot the cost function. So there's also a way to plot these 3-dimensional things, which is also this pie plot here. And well, I will not go through in detail through this code here, but this is just maybe not the best way, but this is just how you can plot these data points. And what we get in our example is this graph here. So we see here, so this is the cost. Oh, loss function. Cost function. Sorry. So this is a cost function j, which depends on theta 0 and theta 1. And the blue dot here is the position of our best possible theta 0 and theta 1. So here this theta 0 was 6 point something, and this theta 1 was 1 point something. So we see here also visually that the cost function at this point has its minima. And for other thetas, the cost function gets bigger. So one question is how to find this file. So this file I posted in the Discord, in the main chat. So if you want to play around with this file, it's on the Discord. And maybe later, after the lecture, I will also put it on the homepage. Okay. And maybe someone can put maybe the link in the Zoom chat. Maybe some of the tutors would be nice. And yeah, so this is the cost function. And now we want to use this gradient descent. So we will start at some theta, because we don't know the blue point. We cheated to get the blue point. So and we want to start at some random theta, for example, at 0 and 0. So we will start somewhere there. And then we want to go down slowly to reach this blue point. Yeah, so now you can find the link in the Zoom chat for this document here, and then you can play around with this. So, and to do this, we introduce this gradient, which in general was given by, oh, here's the same typo. So let me check. Then you can also see. So you can see here in Google Colab, you can also implement, you can write some LaTeX. And then you can remove the typo here. And yeah, so this this gradient was given by these partial derivatives. And in the case d equals 1, we saw that this gradient is just a vector of size 2. So here, now I write it to make it a little bit clearer. So this j depends on this theta, but this theta is just theta 1 and theta 0. So it's a function which depends on these two variables. So I can take the derivative with respect to the one variable and with respect to the other. And then the first entry was just given by this. So here we have a 1, which corresponds to x0. And here we have this x. And now we want to implement this gradient here to then use the gradient descent. So here's again, I mean, this is redundant, but I put again here the training set. And then the gradient, which is now again a function, which depends on some theta. So this is just, so the G0 is the first entry here, and G1 is the second entry. And I want to take the sum over all trainings examples. So therefore I take the sum here, where this J runs from 1 to n. And in the first, I just take the hypothesis at the current, at this theta here, which we plug into this function. And then we plug in the trainings feature, and we subtract the trainings label here. And in the second entry, we do the same, except that in this second entry here, we also multiply with the trainings feature. So this is exactly the implementation of this formula here in Python. And what I do here in the end, which I didn't mention in the lecture, is I also normalize this vector. So usually this gradient shows in the direction of the steepest ascent, but the length of this vector also indicates how steep it is. So if it's really steep, then this vector is quite long. And if it's quite flat, this vector is quite short. But what we are actually just interested in is the direction. And therefore, what I do here, I normalize this vector. So this vector, no matter how steep this is, I always normalize to have length 1. and you learn in linear algebra to normalize a vector, you divide by its norm. Of course, you would need to check if this is 0 or not, but for this case now it's okay. So here in this NumPy, there's linear algebra functions which can calculate the norm of a vector. So this is just the length of this vector, and if I divide by the norm, I make this vector a unit vector, which means it has length 1. Okay, so for example, we can check the gradient at some theta, for example, 0, 0. So let me evaluate this and this. So in this case, the theta at 0, 0 shows in this direction here. So if we go up, so at 0, 0, at this point there, it shows in this direction here, as we can see here, because it goes down. Oh, there's also so one question, can we also just have one entry here? But this would actually mean that we do not have any features. So this would mean that our hypothesis is a constant function, which maybe is not the interesting case, because the number of entries here is always d plus 1, and d is the number of features, because this 0 entry is corresponds to this constant term here. So if the entry of this gradient is just has one entry, this means we just have theta 0 here, which just means that that actually the value of the function we are looking for does not depend on anything. It's just a constant function. And then the question, is the norm always non-zero? Or will there be an error if it's 0? So from the mathematical point of view, of course, this gradient can be 0, and the gradient is exactly 0 at the minima of the function. But since, well, it's a good point. So actually one would need to take care a little bit of this case here, but actually there's not a real 0 inside Python. So it can be that this norm can be really, really small, but it will not actually be 0. But of course, theoretically, it could happen that there's 0, and then we would divide by 0 and we would get some error. So maybe here one needs to be careful a little bit, but usually for real life data, this would actually not become 0. It would just become a really, really small number. Yeah, thank you for the questions. Okay, so at this case here, we get this gradient. And now we want to implement this gradient descent. And we saw that one step in this gradient descent is we start with a theta and then subtract, because we want to go in the other direction of the gradient. So we subtract a multiple of the gradient at this theta, and this will give us a new theta. And here I just wrote out the formula for the gradient, which we calculated here, but this line you can also ignore. So how can we implement this now? So, well, we start with some theta. In this case, I choose 0, 0. And so this is now just, I want to keep track of the points where we walk around. So this has actually nothing to do with the actual algorithm. But I want to plot in a second also the gradient descent, so we can see how we walked. And here's the learning rate. So in this case, I set it to 0.1, and we will change it and then see the difference, what happens if we change this alpha. And I start with I can also start with 100 steps. So how often do I take a step. And now I just do a for loop here. So this just means I do this here for 100 times. And so the main part is this here. So I say the new theta, I overwrite this variable and say I take the old theta minus, so all of these objects are arrays. So maybe here I could, well, actually in this case it's the same, but maybe it would be better to do it like this. So all of these are, so this theta is an array of size 2, and also this gradient function, which we defined here, the gradient function takes a vector of size 2, and it returns a vector of size 2, namely our gradient here. And here, so therefore this is really an equation of vectors of size 2. Or question. In some rare cases, you can actually reflect this. Ah, yeah. So the comment here is that actually it can happen that I get a real 0 and then I get an error. So for example, if I divide by 0, well, in this case, I get this. And maybe here, if the, so let me, yeah, anyway. Yeah, so thank you for the comment. So maybe in practice, one should take care of this, but now it's just for showing purposes, but maybe for real life data, this will not make any problems. And maybe one can check here if at a point where the gradient is already is really small, this usually means that we are already at the point where we want to go, because the place here where the gradient has norm 0 is exactly at the minima. At all other points, the gradient actually has some length, because at other points it goes up or down. So maybe a good check here, and this will be part of the first assignment for you to make a nicer implementation of this whole thing, would be maybe to check if the gradient has a really small norm, and in this case, you're actually at a local minima. So yeah, thank you for the comment. Okay, but now, so here we have implemented this step. And what I do here is just I write down the points where we walk, so I can plot them, but this has nothing to do with the algorithm. And then here, after doing this gradient descent, the values of this theta will give us our result. And then we can compare it with our best theta, which we got from the implemented function. So if I run this now, we see that after 100 steps, we actually don't really have a nice result. So after just 100 steps, our gradient descents gives us the value 0.8 for the first entry and 1.3 for the second entry. But we know the best value is actually this one here. So let's see what happens if we, for example, increase the number of steps and let this run again. Then we see that it's already a little bit, or much better. So the first entry is now 6 point something, and the second entry is 1.14, which is quite close already to where we want to go. But now let's see how this looks like in our explicit example. So there again, this function here is just now to visualize everything. And here you will see I use the data I used here. So in each step, I write down the theta 0 and theta 1. And then here what I do in this function, I just plot the cost function for these points. So if we let this run here, we get this picture here. So I draw, I don't know why I wrote lost function. I want to write a cost function. So we see in our example, we started at 0, 0. So we started here at this point on the cost function, and then we took one step in this direction, because here it goes down, down, down. And then we walked around this path here, and then we almost reached the blue point here. So this is now the movement of our theta. So in the end, the theta was 1 point. So theta 1 was 1 point something, and theta 0 was 6 point something. So now we can check what happens if we again decrease the number of steps. So for example, if we just take 100 steps and plot this again, then we see here, we go here down and then walk around, and after 100 steps, we are just here. And maybe now let's increase the learning rate. So the learning rate tells us how far we walk in each step. So if we take this 1 and we plot this again, we see we start here, we take a big step there, and we take a big step there, big step there, big step there, and we walk around here. So we see in this case, maybe the number of steps is not so nice. And we also see in this case, maybe gradient descent is not really nice, because here it's already quite flat. So the downhill here is not really, it's not really steep. So that's why in each step, we just walk a little bit in this direction. So that's why, in this case, this gradient descent, we really need a lot of steps until we, so now let's take a lot of steps and still big steps. Oh, this we also need to draw again. Then we see that, that we actually, what I mentioned earlier, if the learning rate is too big, we actually do not come close to this, because we always jump around because we take these big steps. So one question is, if you didn't normalize the gradient, how the result changes. So the result, if we don't normalize, so here we see that the step size is always exactly the alpha. But if we wouldn't normalize, then in this case, it's quite steep. So the length of the gradient would be quite big. So in this case, we would actually make a really big step. And then here at this point, the gradient is smaller. So we would do smaller steps. So if we wouldn't normalize, then the steps wouldn't have the same size. And in this case, I think it actually looks terrible, because in this case, these gradients are really, really big. So let me remove this and see what happens. Yeah, but I think already 0.1 is, so let me just do 100 steps. So in this case, actually, the numbers are too large. So this has to do with the fact that these gradients are really, really large in this case here. Yeah, so maybe in your assignment, you can check how, so if I don't normalize this, for example, here, well, in this case, it's not so terrible. But well, at the first step, it's not terrible, because this just says I should go in this direction. But now if I go like this, in this direction, let's say with learning rate 1, and then evaluate the gradient, then I get this. And then I would walk again by big steps like this. And then, so you see that in this case, the gradient are quite large. And then already in the first step, I jump out of this function where the value gets even larger and steeper, and then the gradient is even larger. And then maybe after 10 steps, I get an overflow. So yeah, so that's why maybe we keep the normalized version here. Yeah, thank you for this question. Oh yeah, so, okay. Yeah, so one comment, I think not normalized gradient with small learning rate is also usable. Yeah, so we could really make maybe this this learning rate here really, really small, so that in the first step, we don't really jump out into the jungle. So, and then it should maybe also work, because then it keeps around the place where the values are not so big. Yeah, so maybe if you open this notebook, you can play around and see if you remove the normalization here, maybe choose a really small alpha, then it should also lead to a good result. Okay. Yes, so this is the gradient descent. And one idea of the homework assignment is that you implement this not just for one feature, but also for more features. And then you will also learn how to use actual real data, which is more interesting than this Tebasaki example. So there are a lot of free data sets out there which you can use to learn machine learning. And maybe, for example, one standard one is this house prediction one, where as features you have the size of an apartment, maybe the walking distance to the subway station, and the area, and so on. And so there are a lot of features which influence the price of an apartment. And then you can use this real data and implement this linear regression using gradient descent to make some prediction, and then compare these prediction with maybe other data points in these data sets. Okay, so this was gradient descent. Maybe we will do more examples like this. So what I want to do now is talk about, well, we don't have so much time left, but as I mentioned at the beginning, that there's a direct way to use linear algebra to solve this linear regression. Okay, so now let's recall some linear algebra. And I know some of you did this together with me, and maybe some of you did it with Eric Dapeux, and maybe some of you did it in their free time. So so in our case, what we wanted to do is actually wanted to solve a linear system. So assume that we have the situation that our training set, that all these points, maybe they, if I have here an x1, x2, x3, so it could be that they all lie on one line. So this is our h, and here are the corresponding y1, y2, y3. And in our example, this h is theta 0 plus theta 1 times x. So if they would all lie on a line, these training examples, then these thetas would be a solution to this equation here, because I mean, if I multiply this out, so this you learn at the beginning of linear algebra, for example, the first entry here is exactly theta 1 times x1, up to theta 0 plus theta 1 xn. And so these are exactly h theta x1 up to h theta xn. So if they lie all on a line, then we have this equation here. So in other words, if we call this a, and this theta, and this y, then we have this equation, or this linear system, and that the matrix times this vector equals y. But of course, in applications, like in our Tebasaki example, this is not the case. So they do not lie on a line. So, so the statement is, Of course, usually this is not the case. So like we had before, we have points like this, and they do not lie on a line. And therefore, this equation here does not have any solutions. Because if this has a solution, then there would be a line, because with just two parameters, this h is just one line. So usually we cannot solve this equation usually. But what we want to find is actually, well, we cannot find a solution to this equation, but maybe there's a best possible choice for these thetas. And by best possible, we mean that we want to minimize this a theta minus y. So if this has a solution, then this would be just 0. But instead of trying to make it 0, we just try to make it small. And in this case here, this this notation here, this if I have a vector with entries v1 up to vn, then this norm is just the Euclidean norm, which is given by the square root of the sum of the squares of this vector, of the entries of this vector. And in the case when n equals 2, so if I have a vector of size 2 here, v, then the norm of this vector is just the length of this here. So this is the norm of v. And also in R3, the norm is just the length of this vector. So what we want to do this here is a vector of size n. And we want to minimize the norm of this vector, because then this corresponding theta is then somehow the best solution to this unsolvable linear equation. But I already see that the remaining time is not enough to do it in detail. So maybe I just give the theorem for free, and then we will do this a little bit also again next time. And the main theorem is that to minimize this expression here, so the best possible choice of this theta is given by those thetas which satisfy this equation here, where this AT is the transpose of A. So if this here is A, then the transpose of A, transpose just means we change rows and columns. So in this case, the first column of A, which is just these ones, so these correspond actually to this x0, the first column just becomes the first row. So here this A is a n by 2 matrix, and the transpose will be a 2 by n matrix. And here the second column becomes the second row. So here it's x1, x2, and so on. And this matrix here, the transpose of A, this matrix times this matrix, this is a 2 by 2 matrix, because if I multiply this matrix with this matrix, so if I multiply a 2 by n matrix with an n by 2 matrix, then the result is a 2 by 2 matrix. So this guy here is a 2 by 2 matrix. So I have some 2 by 2 matrix with some entries, and I want to find a theta such that theta 0, theta 1 equals, and here I multiply this vector y with the transpose of A, this one here. So if I multiply this vector with this matrix, this is also a vector of size 2, so this will be some vector of size 2. So we see that here in this case, I really have I just have two equations I need to solve. And usually there's always a solution. And by usually, I mean that or maybe some of you remember the kernel of a matrix, but now you don't really need to care because this is usually satisfied. This just means that the rank of this matrix here is 2. And usually this will be the case because I just have 2 columns and a lot of rows. So this just means that these 2 vectors are linearly independent. Oh, there's just one question. If we have unlimited time, is the lowest learning rate always the best? Well, in this case, yes, because you then get the most precise result in the end. But in real life, you don't have unlimited time. But yes, the answer is yes to your question. But here again, so the statement here is that if we can find a solution to this linear system, then the solution of this linear system will actually give the best possible choice for these thetas, meaning that this minimalizes this thing here. And this always has a solution, meaning that this matrix here, this 2 by 2 matrix, is always invertible if these 2 columns are linearly independent, which in fancy terms, you can say that the kernel of this matrix is trivial. But ignore this, because this is usually satisfied. And the statement is that in the end, you can get an explicit formula for the theta by solving this linear equation, meaning you can multiply with the inverse. So you can multiply with the inverse of this matrix with this vector here. And time is running. So maybe at the beginning of next time, but also here, I sketched a little bit how the proof of this works, but this I will do next time. But I want to show this in Python so you can believe me that this theorem actually works. So this formula here gives one explicit formula for the thetas we are looking for. So here, using linear algebra to find our thetas. So this formula here is now the formula which we didn't prove yet, but which we now take for granted for now. Oh, and here's also one example I wanted to do in the lecture, but let me skip directly to our Tebasaki example. So in our Tebasaki example, our matrix A, where the first column is always 1, and the second column contains our features, which were 2, 7, 13, and so on. So these are the weeks living in Nagoya. And our y vector contains our labels. So these are the number of Tebasaki. And then according to this formula, where am I? To this formula here. So we want to multiply this matrix here, A transpose A, takes the inverse, multiply with A transpose and times Y. So this is just one formula here. We take A transpose, so the product of a matrix with a matrix in NumPy is called the function dot. So this is a transpose, and the matrix has a function called dot. So this is A transpose times A. Then I can take the inverse of this. This gives a matrix, and then I can multiply it with the transpose of A. And this I can multiply with the vector Y. And then if we do this, well, you already saw the result, but here we see that actually this one-line formula gives our theta 0 and theta 1. And these are the ones we saw before. Yeah, I think we had theta 0 and theta 1. Yeah, so these are actually exactly the same. Maybe here's just some rounding up. Yeah. Yes. So here the 7 rounds this up to a 2. Okay. So maybe this is enough for today. So I will stop recording, and then you can still ask some questions.